My name is Yuzhu Lu, and I worked on front-end graphics for many years. So today's topic is GLSL support with Mathematica Graphics. Okay, what is GLSL? It's OpenGL Shading Language for those who don't know, and it is a language you could run on GPU hardware directly. So before I start, I want to talk about something else, graphics feature development. And whenever we discuss adding or implementing new features, there's always a long list and so many requests. Everyone has something they want. And due to the limited resource, we have to give the different priority to each of them. Those low priority requests might have very low chance to be visited. So now let's come back. So it's about, today I'm going to talk about something about surface appearance. It's a new feature that could help for that kind of a situation. So what is surface appearance? It's a little bit different from the previous features we had. The previous features is either like let user pass in a collective data, for example, positions, colors, normals, or predefined behavior, a certain light or certain shape. But the surface appearance is a little bit different, and it allows the user to pass in a piece of code, and the code is defined by user. So basically means user could decide what the graphics would renders, or what it look like, or maybe whatever you wanted it to do. Even though surface appearance still stays experimental to our user, internally we have been using it for development, and many of the released features are built on top of it. So I'm going to give a little introduction about the surface appearance itself, and then show you what you can do with it and the benefits of that. So here's a list of things we already released, or we're going to release for version 13, and which are built on top of surface appearance. Some of the features are pretty tricky, for example, like a material shading. And Charles and Alec did an amazing job, and they ported the whole Google's Material X library. So that is material shading. And if you take a look, it is using surface appearance. And Alec just had a very nice talk about this material shading. If you're interested, you can visit his talk video. And also the solid region. This project could be very tricky as well. And it's going to release, released with version 13 as well. And the things it does is it will use the ray tracing method. So before that, all our models are surface models, same as like 99% of the rest of the applications. So that means if you cut the empty, it's empty inside. But the solid modeling is a little bit different, and using ray tracing method, and to decide each pixel if to see it's inside of an object or it is outside the object, and decide what kind of property it should use, like colors. things like that. So the surface parents allows you to pass in the GLSL programs. So here is the syntax, and it's pretty straightforward, and you can just you need to give the name, because with the name you can call it later, and you can also tell the program what kind of data you're using. For example, like the vertex position and text coordinates, normals, things like that. The vertex position and the text coordinates are always generated for both 2D and 3D, all face-based primitives. Normals are generated for all 3Ds, so it's safe to use. And you can also pass in parameters. There are different types of parameters, and these are to match the types which could be recognized on hardware, like GPU. And the difference between attribute and parameter is attribute usually is a huge, a bunch of huge, it's a bunch of data. And the parameter, usually the data size is much smaller. For example, like colors could be shared between all the data. And there are a list of things predefined you can use. For example, like for matrix, these like a predefined values. And I just attached this documentation together with my talk, and I will upload this notebook as well. You can, for your reference. So I just take this as an example. This is going to be very useful, and it will just make your application work with the, for example, like resizing or static graphics in another graphics. So let's take a look at the real example. And here I'm going to define a customized texture mapping, which we don't have. It's turning into gray level and then maps the gray level texture. And give the name, and you tell the program that you're going to use the position and the text coordinates. And parameter is the matrix, so it could be resized. And also, the most important, you need to pass in the GLSL programs, including Fragment Shadow and the Vertex Shadow. What does the shadow look like? So just as to match the interface we just mentioned, so it will declare the position and text coordinates you're going to use, and you're going to output the text coordinates and used by Fragment Shadow. This is a Vertex Shadow, and apply the matrix, and then this is Fragment Shadow. So we just use whatever we generated from the Vertex Shadow, that is a text coordinates, and then we are going to apply the gray level, sample from the texture, and apply the gray level, and then write to the color. So simple enough, and let's see how it works. After you define the code, you need to add it to the library. Like you can add multiple times the same name, so the newest one will be active. So we add that. You can also check if the definition has been added successfully or not. And if it's successfully, it will print out all the information it has. If so, otherwise, it will give failed. So to use it, you just use the surface parents and give the name of the shadow you're going to use. And we will look it up in the library. And also you can also pass in the parameters. So this is customized text mapping. You can do more things than that. And I will list some of the example here. One of the first example is digital arts. And if you're looking around, and there might be some, here is a blog post, and they are posting some very neat digital arts and implemented by WebGL. And they show all the code here. And I will just take that and see how that works with Mathematica. And so I just download that and save as a GLSL file, and just same as the previous example, I just tell to use position, text coordinates, and the matrix. Other than that, I will also pass in more uniform that is parameters time. So it evolves as time goes, and also tell the program the size. And so here it is. So it just ported and straightforward enough, and it just works. And it changes as time goes. So, and we can do more things than that. This code is from one of our active user, Mike Salami, and I helped him to port his Code Life project, and his project is trying to write some a music visualizer. So here it is. So there are two parameters. One is the time. As the time goes, it changes. So you can see the flow. And also there's another parameter, which is you could let you specify a spectrum, so you can feel the beat. So yeah, so I'm not going to upload this part of code. If you're interested, you can talk to Mike. And so yeah, that's so. But the code project itself is it's a little bit more than that. It does multiple paths. So I just show how we can do with the second pass. So we can just use, for example, this second pass is just does some image processing to make it look brighter. This is the original one, and this is the after process. And still having the parameters working. And what we do here is just we rasterize it to give it to a texture, and then use that as texture as the input for the second pass. So, but this is not just the end. And we want to connect with the sound, so it could jumps with the music plays. And so here it is. We just loaded the example audio drums and make a simple music player. See, you might not hear the sound, but you can see the numbers jumping, and this the visualizer is could help to visualize the jump as well. Okay, so that's another example. And GPGPU. So we had a bunch of Julia factor functionality. But what I want to show you is that these are computed in the kernel. But what I want to show you is that how to do that, move the computing to GPU. So here it is. The benefit of that is the computing happens on GPU and it's pretty fast. And if we want to show some animations, and it will be real time. So also, other than you can pass in the GLSL file name, and you can also pass in the code itself as well. So the notebook could be more compact when you send it to other people. Otherwise, you have to send the GLSL file separate as well. So this is it's more compact form, and the GLSL, the benefit of that is the code is more readable. So when we're talking about the GPGPU method called ping pong method is one of the key techniques for many GPGPU applications, and also for those physically based simulation. For example, like we want to add 1 million float numbers. You could feed those million data into a texture 1000 by 1000, and then you can using the shadow to do the reduction and reduct to 100 by 100, and then 100 by 100 reduct to 10 by 10, and then into 1. And the shadow, it does just adding the subset of the subtextures like a 10 by 10 into 1, and the algorithm is simple add. So this way you can move all the computing from CPU to GPU. And the same thing, like for example, the physical based simulations like two galaxy colliding. So the current status is based on previous status. So which means you have to have two textures which were flipping with each other. And the difference compared to post-processing is post-processing just 2 paths or 3 paths. But like this could do it can do unlimited paths. So here's an example how do we can do that. And the example here is just we adding a point from the mouse, and the processing is just taking the previous texture and then fade it using Laplace filter. So you can see it just faded away and gradually. And if you look at the code here, so the previous texture is rasterized based on the current texture, and the current texture is based on the previous texture. They are kind of dependent on each other, and so this way you can just keep doing the infinite loop. So another example is we could apply a video object. We have a very nice video feature coming in version 13. And here I just want to show you that video could be expensive, but we could apply some like video effects and very low cost video effects. What it does is kind of like a post-processing. And this page posts a bunch of examples. Here I just imported some of them and save as a GLSL And let me show you here. So it just running real time. What it does just when it is showing the video, it just apply the different shader. And this is a twisted lens. Let's see. It's a pretty big video, and let's see. Check the size. It's like, yeah, it's HD, but it's still real time. So it's not passing the data. It's not passing the pre-computed data. It's just passing a piece of program. Next, you might think, what else we can do with it? What if we don't have GLSL file resources? And we could have the code to generate GLSL files. So, for example, I just take a template here as an example, and this is slot here, and you can use it to generate different functions, different GLSL files. For example, here it just converted the function and replace with that to build a customized GPU-based density plot. So here's an example. So it's the density plot happens on GPU, and if you take a look, you will see that a new shadow is generated, and when we look at this code, and instead of the slot, it replaced by something you defined, and so if I run something different, it will generate a different GLSL file here. You can do a lot of different things. For example, so these are operations could be recognized by GLSL, and potentially in the future you could did a map between our top-level code and to the operators recognized by GLSL, and then that way we could compile our top-level code into GLSL code. So if we take a look, see, there are more GLSL code generated. So next, there are so many different hardwares. There are different platforms, and there are different drivers. So how can we make our program could run all machines? So now we are recommending to use the GLSL 3.3 standard. You can also use the other standard, different versions, lower than this, higher than this. It totally depends on hardware. If your hardware support that, it should just work. If not, we will try to convert it to the version is supported. So the way we deal with that is just what you're passing is just black box. We pass it along to hardware and then collect information from the hardware. Sometimes hardware are not happy with that, and we just give error messages, and this error message will will be sent to message window. And this is extra useful when you are doing debugs. And if there are some errors or warnings there. And so how to find out what kind of version your drivers support? And here are some utilities you can use. Here are two drivers available. One is hardware from NVIDIA. The other one is from Mesa. And the Mesa one is 3.3. And that is why we said that we recommend using GLSL 3.3. And that is, in any case, all platforms with Mesa could be a fallback. And for other versions, it might still support, and it might not. So there's another utility you can use to tell if your version is supported on the hardware. And so here, I just say version 480, and it is not defined yet. Of course, it won't be supported. So it gives you information and from the message window. And so when you are doing GLSL programming, that's some useful feedbacks you get. And you will also see it fails to render. So, and since we are passing the piece of code as black box, and sometimes GLSL compiler from hardware is quite picky. Some of the symbol we copy from, for example, like backslash 011, some of them are invisible, but that will make a GLSL compiler very unhappy. Sometimes it might not give very useful information, error messages about that. So to use a plain text editor will be very useful, and visualize that and remove that. And it makes things easier. When you are using something copied from somewhere else like web. And there are a few mistakes you could make for different versions. Some of the drivers will support autocast between integer and float, and some of them are not because they are not defined by in the spec. But the vendors like NVIDIA and AMD, they think it's probably more friendly to make it allowed. So to be to be safe, you want your code could run all cases. It's better do not do the autocast. And also texture 2D is deprecated by texture in GLSL 3.3 and after. And some of them must still support it, but some of them were not. And because it's not defined in the spec. And so if you are using different versions, include that version, otherwise it will think it's just GLSL 1.1. And also you might have to define integer and float precisions for OpenGL ES and WebGL. And in the future, we're going to support. And some of the precisions like high precision, medium, and low are only supported. There you have to make sure you have macros checks if only GL ES available, then you use that. That helps to reduce the errors you can make. So what's the benefit? What do you get from this? As I mentioned previously, you can do customized rendering. You can decide what the graphics looks like. And so you make the decision, and the code is totally defined by you. You have the control. And you can also, for some features that is unique only by you, and only the notebooks from you. And again, if you have a bunch of GLSL resources, and you can reuse them easily and make it work in with your mathematical code. And as I mentioned before, the difference of this surface appearance is it does not pass the data, pre-computed data. It just passes the code itself. So it could be helpful to reduce the CPU cost. And for example, some of the pre-computed colors, you could be avoided, and you just do it on the fly. And the same thing, if you don't compute it, do pre-computing, you probably don't need to transfer those data, and could reduce the memory consumption and increase the performance. Last, it could also, like I mentioned before, help for the cases, for the situations of adding new features. There are two logic behind that. With surface appearance, and more people could contribute. And the real example there is Alec and Charles has been effectively working on many of the fillings and the shadings there, and it just not just front-end people can do that. Even active user can do that as well. So another logic behind that is I will use my own example that a couple of years when I do the depth peeling development and the prototyping, it took me 1 month to make it work on one machine. But it took me 10 months to make it work for all the hardwares, for all the platforms. So with this GLSL support, you just make it on one machine. It's our responsibility to make it work on all machines and all different platforms. That's why it could reduce from 10 months to 1 month. And so yeah, that's my talk. And let's go to if there's any questions. Does the shadow processing always has to happen through front end? Yes, the shadow is always happened in the front end, but you can do something else. For example, like some of the some of the CUDA link that is doing something else. It's because it's not using front end. But if you are using some front end primitives, yeah, the shadow is always going through front end. Yeah, the Unity and the Unity link is same as the CUDA link. It's not using front end at all. Okay, so it's 12:34. So if you have more questions, and please drop me email and leave something in the chat. I can answer the questions later. So okay, let's enjoy the talk and enjoy your rest of your talk. Thank you. Bye.